In this video, we will see some examples about singular points of differential equations. Example 1. We need to find all singular points for this equation and classify them as regular or irregular singular points. Recall that to determine the singular points, we need to get it from the leading coefficient. And to classify the singular points, we need to check out two limits from the coefficients. So to make it easier for the reference, we're going to denote the three coefficients as P, Q, and R. So that's the coefficients for the second derivative, first derivative, and zeroth derivative terms. And to find the singular points, we just need to make the leading coefficient equal to 0. And in this case, you're going to get x times x minus 1 is equal to 0. And easily, you can get x is either 0 or 1. So for this equation, we're going to have two singular points. And to determine whether or not each single point is regular, we need to check two limits. So for the first one, x is equal to 0. We need to check q over p, the corresponding coefficients, and then times x minus the singular point 0. And then you take the limit for x approaching the 0. And for this case, we simply plug all the expressions in and do the corresponding cancellations. We're going to say this resulting function is going to be just a constant. So the corresponding limit is also a constant 3. The second limit problem is we have to check r over p and then times x minus the singular point squared when x approaching to the singular point. And once again, you're going to plug all the expressions in and do the corresponding cancellations. And then you're going to end with this expression. And for this expression, when you put the 0 in, the denominator is now 0, so it's well defined. And then you can simply evaluate this function. That will be the limit. And for this case, you're going to get 0. So for both limits, we get some finite values. So therefore, we know the singular point x is equal to 0 is a regular singular point. For the second singular point, you're going to do the same thing. Okay, for example, for x is equal to 1, you're going to do the q over p, and then x minus this point when x approaching to this same point. You plug all the coefficient functions in, okay, the coefficients q and p, and then you do the corresponding cancellations. We're going to end with this function. And now when you put the 1 into the denominator, it's now 0. So this quotient is well defined. Okay. So then you just evaluate it, and then you can get the limit is going to be simply 0. For the second limit, you're going to check here, it's x minus 1 squared. Okay. And then you plug all the coefficient functions in, you do the corresponding cancellations. And here, you can see here when we change the, x minus 1 to 1 minus x, we are taking the negative sign into consideration. Okay. So after the cancellations, you put the negative sign in, you get 1 minus x. But anyway, for this function, when x approaches 1, you're going to say it's going to be 0. So now, because both limits, they are finite, they exist, so we know the second singular point, x is equal to 1, is also a regular singular point. Example 2. So this time, we're going to do the same thing. Okay. Again, you need to find the singular points and classify them. So once again, so to make it easier to refer to the coefficients, we simply define them as P, Q, and R. And we know the singular points are coming from the P is equal to 0. So that for this case, you're going to get the x minus 2 squared times x plus 3 squared is equal to 0. And from the zero product principle, you can get your x is going to be either 2 or negative 3. So we have, again, 2 singular points. And to classify them, we need to once again check the 2 limits for each of them, right? So for x is equal to 2, you're going to do the q over p and x minus the 2 as x approaching to the same point 2, right? Now you plug the coefficient functions in, you do the corresponding cancellations, and then you end with a function which is well-defined when x approaching 2, right? So you simply evaluate it, you're going to get a finite value 4 over 25. For the second limit, we'll do similar approach, right? So we simply plug the coefficient functions in, do the corresponding cancellations, and then you're going to end with, again, a well-defined function as x approaching 2. So the corresponding limit is going to be another finite value. So because both of the limits are well-defined, we know the x is equal to 2 is a regular singular point. For the second singular point, well, we check the 2 limits. For the first one, you can say here q over p as x minus singular point negative 3. And here x approaching to the singular point negative 3, right? And now we plug once again the coefficient function in, and we try to do the cancellations. And then you're going to say 4 over x minus 2 times x plus 3. For this limit, as x approaching negative 3, you're going to have a 0 denominator. But the numerator is a constant. So a constant over 0, we understand this is undefined, right? It's undefined. And because one limit is undefined, you don't have to even check the second limit. We understand the x is equal to negative 3 is going to be irregular, okay? So we're going to have, for these 2 singular points, one of them is regular. The other one, the x is equal to negative 3, is irregular. Example 3. Well, we have a similar problem here. So once again, we need to determine the singular points and then classify them. So here we define the coefficients as P, Q, and R again. And we know the singular points are coming from the leading coefficient is equal to 0. And for this, you can say, actually, when I write my P of x here, the leading coefficient here, I already factored it. Okay, so the x squared minus 1 can be factored as x plus 1 and x minus 1. And because you raise it to the second power, so you're going to say these 2 factors are also raised to the second powers, right? Similarly, for the x squared minus 25, you get the same thing, okay? So we know P of x is equal to 0 gives us this equation. And from the 0 product principle, we understand each factor could be 0. So therefore, you can get x is going to be plus or minus 1 plus or minus 5. Okay, so we're going to get a total of 4 singular points in this case. And we need to check the limits for every one, right? So let's see. For x is equal to 1, you're going to use a q over p times x minus the 1 here, right? As x approaching 1. You plug the coefficient functions into this expression. You do the cancellations, okay? So for this part, you're going to get x plus 1 canceled, x minus 1 canceled. So you're going to still have 1x plus 1 times 1x minus 1, which will give you x squared minus 1. And for the other one, we understand these two x plus 5 and x minus 5 will give you x squared minus 25, right? So we can write it in this form. And now we understand when we put the x is equal to -1 into this expression, it's undefined because you have a 0 denominator, right? So therefore, we know this is going to blow to infinity in this case, right? But infinity is undefined, okay? So it's not a finite value. So therefore, we understand we don't have to really check the second limit. We already know this x is equal to 1 is an irregular singular point, okay? To be a regular singular point, you have to have both of the two limits are finite. If one of them or both of them are undefined, then you know it's irregular. Okay, so now we just need to do the same thing for the other 3 regular points. Okay, so now let's check out x is equal to -1. So once again, you're going to use a q over p times x minus -1 as x approaching to -1. You put all the coefficient functions in, you do the cancellation, and then you will say for this function, when you put the -1 into the denominator, it's not going to be 0. So whatever value you have, that's the limit. And then for the second limit problem, we pretty much just plug the corresponding parts into the expression, right? And we do cancellations if it's possible. You can say here x plus 1 squared, right? And x minus 5, right? Yeah, cancel one of them. And then you're going to say this, again, is going to be well-defined when x is equal to -1, okay? So therefore, we know the corresponding value is going to be the limit. So because both of the limit problems, they are well-defined, they exist. So we know that x is equal to -1 is a regular singular point. Now, for x is equal to 5, you again try to check the q over p times x minus the singular point as x approaching to the singular point. And you plug the coefficients in, you do the cancellations, okay, x plus 1 cancel, right? X minus, actually here, I didn't really cancel it because we noticed that we have some trouble here, right? So we just cancel one of these because, you know, the x minus 5 as x approaching 5 is the concern, okay? Yeah. So you will say all the other terms, they are well defined, okay? They are not going to give you 0. But the x minus 5 as x approaching 5 is going to be 0. So we know the whole denominator is going to be 0 when x is 5. And therefore, you can have a constant over 0, which is undefined. And we know if one of the two limits is undefined, then this singular point is irregular. Finally, we check the same thing for the x is equal to -5. Once again, q over p. And then you get the x minus -5 as x approaching -5. So in this case, you can say we're going to get x plus 5, cancel one of the two x plus 5s, but you still have one x plus 5 left. This guy is going to be 0 as x approaching -5, right? So therefore, you're going to get, once again, a constant over 0, which is undefined, which means the x is equal to -5 is also irregular. Example 4. So once again, we need to find the singular points and classify them for this differential equation. So here we're going to let the coefficients be p, q, and r. And here you can see I did a little algebra, right? For similar reasons in example 3, because later on, you have to factor the coefficients to do cancellations. Okay, now we know the singular points are coming from the p is equal to 0. so that you're going to get this factored form is equal to 0, right? So easily you can say the two singular points are 0 and 1. And now for each of them, we need to check two limit problems. Okay, for the first one, when x is equal to 0, you're going to use Q over P times x minus 0 as x approaches 0, right? You need to check out this limit. We plug once again, the coefficient functions in, and then here x minus 0 is simply x. And you can do some cancellations, right? And for this one, when you check the value, you're going to say the denominator apparently is going to be 0, right? But the top is also going to be 0 because the cosine 0 is 1. So 1 minus 1 is going to be 0, right? So we have a 0 over 0 pattern. If you have some non-zero constant over 0, we understand it's undefined. But when you have 0 over 0, we have to pay extra attention, right? So for this case, we're going to use the L'Hopital's rule, okay? L'Hopital's rule says the limit of 0 over 0 pattern is going to be equal to the limit of the quotient of the numerator's derivative and the denominator's derivative. So basically, you can say this is the derivative of the numerator. We are using the product rule here, okay? So the first factor's derivative is a positive sign, right? Because you have a negative sign in front. And then you times the second factor. And then we get the first factor times the derivative of the second factor. So you're going to get the twice of x plus 1. And then the derivative of x plus 1 is going to be 1, right, with respect to x. For the denominator, product rule again, you're going to get the derivative for the first factor, 2x times the second one, right? And then plus the first factor times the derivative of the second factor, which is 1, right? So you're going to get this. And now when you check the value of this, you're going to say the denominator again is going to be 0 because you have 0 right here and 0 here, right? So 0 plus 0 is going to be still 0. But when you check the numerator, you're going to say sine 0 is 0, right? So then the whole thing, the first term is 0. And here, cosine 0 is 1. So 1 minus 1 is 0. So then you know the second term is also 0. So it's 0 plus 0, which is also 0, right? So once again, we have the 0 over 0 pattern. Means we have to apply the L'Hopital's rule again. So here, basically, what we have over here is just a second application of the L'Hopital's rule. So you can say for this part, you can say the sine derivative is cosine, and then you have the first vector, right? And then the second part of this actually is combined over here. This term is a combination of the second term here and the first term here. Okay, so basically, once you take the derivative of the numerator, you're going to get this. And the derivative of the denominator, you will say is going to be 6x minus 2. Okay, now for this case, you're going to say the denominator is no longer 0, right? So that means it's going to be well-defined. No matter what the numerator is, you just use whatever value you got, or the value from the denominator, which in this case is negative 2, right? And then you can end with negative 1/2. So that's the first limit problem, and it's finite. And then we can check the second one. This is R over P, and then times you're going to get the x minus singular point squared, right? So in this case, once again, we first of all do all the possible cancellations, right? And then we're going to say, okay, we have a log function over this after the cancellations. Well, but for this case, the denominator, if you check the denominator, it's not going to be 0. So we can just go ahead and evaluate this function, okay? And that will be our limit. And it turns out when you evaluate this, the numerator is going to be log 1/3. The denominator is going to be -1. So that's why you're going to get a negative log 1/3 But we understand the negative sign can be put inside as exponent, right? So you're going to get a log of 1/3 to the negative first power, which is log 3. Well, now we got both limits are finite, right? So we know x is equal to 0 is a regular singular point. Now we need to check the other point. When x is equal to 1, you check the first limit, the q over p times x minus singular point 1 as x approaching 1. And we can do some cancellations, right? So you can say when you put all the coefficient functions in, you can cancel the x minus 1 parts, right? Totally. And then you're going to end with something like this. And when x approaching 1, we know the denominator is not 0. So this whole thing is going to be well defined. So whatever you're going to get from the function will be our limit. It turns out to be 4 times of 1 minus cosine 1. Okay, for the second limit problem, once again, we're going to put the coefficients functions in, right? And then we try to do the cancellations. So you can say 1x get canceled and x minus 1 squared get canceled, right? But you still have x minus 1 left. Well, in this case, when you put 1 in, you say the denominator is 0, right? And when you put the 1 in, the numerator, you also say a 0 because log 1 is 0, right? So here you're going to get a 1, okay? So for the 0 over 0 pattern, we have to use L'Hopital's rule. So you can see here, I'm going to check the derivative of the numerator. Here we have to use the chain rule, right? So you're going to see the derivative of the log is going to be the reciprocal of the input. And then you have to take the derivative of the input, which is going to be 4x over 3, right? The derivative of the 2x squared is 4x, and then times a constant over 3, right? And for the denominator, its derivative can be obtained from the product rule. Now, for this expression, when you put 1 in, you're going to say the first factor of the denominator is 0, but the second one is not, right? So this denominator is not 0, means you can simply evaluate it, right? So you can see here, when you put 1 in, I'm going to just get the numerator. Here is 3 over 3, which is 1, times 4 times 1 is 4 over 3. So it's 4/3. And then over, we just mentioned 0 and 1, right? So the limit eventually is going to be 4/3. So now we got both limits are finite. So therefore, we know the x is equal to 1 is also a regular singular point. Example 5. Okay, now it looks like we have a easier problem. The coefficients here looks kind of easier, right? Well, but anyway, we're going to do the same thing. First of all, we're going to call the coefficients P, Q, and R. The R here is a constant 1, by the way. And also we know the singular points are from the P is equal to 0. But in this case, when you solve the x sine x is equal to 0, you're going to get x is equal to 0 from the first factor. And from the second factor, x sine x is equal to 0, you're going to get x is going to be a multiple of pi. Okay, it's an integer multiple of pi. And this actually contains the 0 case. Okay, it contains the 0 case. Okay, now when we check out the singular points, although the second case contains the 0 case, but when you check the coefficients, you will say, well, there's still some difference because you say for example, P of x, when x is equal to 0, you're going to say the 0 and the pi, k pi, okay, they have different kind of performance, okay? So that's why you can see here, I need to check the singular point 0 and the other singular points, namely some multiple of pi. I have to check these two separately, okay? Just from the coefficients, you can tell that, okay? So that's why you can see here, I'm going to first of all consider when x is equal to 0. So once again, you get the q over p, x minus 0 here, right? As x approaching 0, you plug all the definitions of the coefficients in, you do the cancellations, and then we get this very famous limit problem, right? We know this is going to be 1, right? And when you check the second limit, you're going to get r over p times x minus 0 squared. And once again, you plug everything in, right? All the definitions of the coefficients, and you do the cancellations. And again, you're going to get the same problem. And this one is also 1. So therefore, we can conclude that x is equal to 0 is a regular singular point. Okay. Now let's say, how about the other singular points, namely non-zero multiples of pi? Okay, you can see here, k is just any integer except 0. Okay, so now we're going to check the first limit problem. We got q over p times x minus k pi. Once again, you plug the definitions of the coefficients, and there's no I mean, you can cancel the x over here, right? Yeah. And you're going to get something like this. For this case, when x approaching k pi, you're going to see the numerator is going to be 0. The denominator is also going to be 0, right? So that means we have to use the L'Hopital's rule to find the limit. So you can see the derivative of the numerator is 1. And the derivative of the denominator is going to be cosine x. Actually, sorry, here is supposed to be x, okay? But as x approaching to k pi, you do have 1 over cosine x, k pi here, okay? And we know cosine k pi actually is going to be -1 to the k's power. Namely, when you have even multiples of pi, you can get +1, and odd multiples of pi, you're going to get -1. Okay, now let's check out the other limit. So you will see for the other one, when you put the like r, p, and x minus k pi squared in, okay? In this case, you're going to say when x approaching k pi, the numerator goes to 0. The denominator, the sign part, also goes to 0. So we have to use the L'Hopital's rule again. So I have to do the derivative of the numerator. That will be twice of this factor. And then times the derivative of this is going to be 1, right? So we don't have to write it. And then the denominator for the denominator's derivatives is going to be sine plus x times cosine, right? And for this case, we understand when you put the x is equal to k pi in, you're going to say the sine part is going to be 0, but the cosine part is not 0, and x is not 0 either. So you're going to get the denominator is non-zero, but the numerator is going to be 0, right? So 0 over something non-zero, you're going to get 0. So we know the other singular points, they are also regular. Okay, they are also regular. Nevertheless, although you know the result is the conclusion here is all of the regular points, I mean all of the singular points, they are regular, but you can see the limits are still different, right? So that's why we still need to like check them separately. And you understand why, right? Because, for example, here you have the cancellation. You can cancel all the x part. But for this case, the x minus k pi, you cannot cancel them, right? You cannot cancel any one of them, okay? And when you do the L'Hopital's rule, you can say here it's no longer 1, okay? So that's the reason. Well, in summary, we understand when we are doing the singular point problems, to find singular points, you just need to solve some equations, right? And to classify the singular points, we just need to do some limit problems. Okay, that's all for this video, and thank you.